Hi everybody, and thank you for your interest in our benchmarking study of sentiment analysis tool for software engineering in a cross-platform setting. So our study fits in the vein of a research trend that emerged in recent years as researchers became interested in the use of sentiment analysis for software engineering application. So for example, correlation has been investigated between the emotion and the issue fixing time and issue tracking system. Other studies investigate the possibility to implement early detection of anger and negative emotion to prevent burnout and undesired turnover. The role and impact of emotion and the emotional writing style has also been investigated in knowledge sharing, for example, in Stack Overflow. And opinion mining is also used for building recommender system for APIs. And another example of application is in requirements engineering, where positive and negative feedbacks in the user reviews is leveraged to prioritize development tasks, for example, where positive emotion indicate desirable feature, while negative sentiment is usually associated to bug reporting. So early studies on sentiment analysis and empirical software engineering mainly relied on general purpose tools that are used off the shelf, so without being retrained. So, however, the reliability of such tools was questioned by studies such as the one published by Jungeling and colleagues. And they observed that such tools not only have poor performance on technical text, but they also disagree with each other. And this disagreement can lead to diverging conclusions. So this is kind of expected, as general purpose tools are trained on corpora collected in different domains, such as movie reviews, newspaper, comments to social media, and so on. So there is a need for software engineering specific sentiment analysis tools, and trying to overcome the limitation posed by general purpose tools, researchers started to develop their own tools, specifically tuned for software engineering, technical document in software engineering domains. So two main approaches prevailed. On one hand, we have supervised learning. So Centi4SD and Centi4CR, for example, implement classification models based on machine learning from a manually annotated gold standard. And on the other end, tools such as CentiStrength, SE, and Deva, which are from the same authors, rely on lexicon-based approach, which means they implement a set of rules and heuristics based on the presence of positive and negative words as they are classified in sentiment vocabularies. So they cannot be retrained, and we use them unless you manually intervene on the rules they implement and you fine-tune the lexicon they use. And so we are including them for reference in our study. So does this solve the problem? In our previous benchmarking study, published at MSR 2018, we investigated if software engineering specific tuning for sentiment analysis tools actually overcome the limitation of general purpose one. And indeed, we found that tuning of tools for software engineering improves the classification accuracy. Specifically, we observed that software engineering specific tuning enhances agreement of tool with manual annotation and with each other. However, we observed such results in a within platform settings, which means training on Stack Overflow and testing on Stack Overflow. So the question remained open related to the off-the-shelf use of such tools. So the question we are trying to address with this study is, can we use software engineering specific tools off the shelf? Which means in absence of a gold standard for retraining, can we reliably leverage those tools as they are, coming with their original classification models? So we formulate three research questions. The first one is, do this tool agree with manual annotation in cross-platform setting? And the second one is, do they agree with each other? So we're basically trying to assess the performance of these tools when used without platform-specific retraining. And then the third question aim at identify the ideal size of the training set for retraining supervised tools. So to address RQ1 and RQ2, we replicated our within platform study published at MSR 2019 in a cross-platform condition. We leveraged 3 different datasets, and we reused Gyra and Stack Overflow datasets, which were previously used in our within platform study. And we developed a third dataset with GitHub Commons for the sake of these studies. So we have overall, in this new dataset, which can be downloaded and reused from Figshare, we have roughly 7,000 comments manually labeled for emotion polarity. The 3 datasets are labeled based on the same emotion model, which is the Shaver model of emotion, where we map positive emotions such as joy to positive polarity, negative emotions such as anger to negative polarity, and neutral polarity refers to the absence of any emotions. So the Stack Overflow and GitHub datasets are well balanced in terms of distribution of polarity labels, while the Gyra one include the prevalence of neutral text. And we also observe a little different in the interannotator agreement, which ranges from substantial to almost perfect for Stack Overflow and GitHub. And we don't have this information for the Gyra dataset from the original author. We only have agreement related to the specific emotion that were labeled. So for training the tools, for retraining the supervised tools, we applied stratified sampling to the gold standard dataset, which we split into train 70% and test 30%. We used the train set to retrain supervised tool, and in particular for Centifer ST, we also trained a little variation of the original configuration because Centifer ST enabled customization of feature set. It includes lexicon-based, so dictionary-based features, semantic feature, and bag of words, in particular uni and bigrams. And we removed these bag of words because we want to test our intuition that this kind of feature are more prone to overfitting with respect to others. We cannot do any of these kind of customization of feature for CentiCR because CentiCR is basically relying only on bag of words. And then we use the remaining 30% for performance assessment, also on the rule-based, lexicon-based tools, which we cannot retrain for reference. And of course, we repeat this process for all the couple of data sets, so train on one data set and test on the other, and to simulate the off-the-shelf use of these tools, so in absence of a gold standard retraining. And the settings on the diagonal in gray, of course, identify the within platform condition where you have data from your own platform and you can't retrain from the very specific data set you are targeting in your study. We assess the performance using standard text categorization metrics such as precision, recall, and F-measure. And we also include weighted Co and kappa. Why weighted? Because we want to differentiate. We want to give more importance to misclassification, more weight to misclassification due to positive and negative disagreement, which we consider as more severe with respect to disagreement with neutral label. So let's answer our first research question. That is, what is the performance of software engineering specific tools in terms of agreement with manual annotation in a cross-platform setting? So in our paper, we have all the detailed information regarding performance metrics. And here, of course, for time constraint, we cannot discuss all of them. So we will simply report F-measure. So let's start from supervised tools and GitHub. And let's assume you have a target platform in your study, which is GitHub, and you have a gold standard for retraining. Now, within platform condition, you would end up observing very, very good performance. Like, for example, we have 0.92 F-measure for Centifer ST and 0.82 for CentiCR. The situation changes when training is performed on a different platform. But training a Stack Overflow, for example, we observe a drop in F-measure of 0.12 and 0.17 for CentiCR, and the situation is even worse when training on Gyra. Interestingly, we observed that in both cases the drop is reduced when bag of words are excluded from the feature set, in line with the fact that the drop is higher for CentiCR, which only relies on bag of word. And this provides evidence of the lower ability to generalize a such feature, and also suggests that some lexical semantics shift occurs across datasets, across platforms, due to platform-specific jargon or communication styles, for example. So this drop in performance is observed for all settings, thus reinforcing the intuition which inspired the study that the concept of domain which is now identified with the software engineering domain, should be probably narrowed down to the specific platform because of the peculiar use of language and communication devices in every specific platform, also with respect to the purpose of the platform. So in particular, we observe that the highest drop when the Jira dataset is used for training, which indicate probably a higher distance of the Jira gold standard from the other two, which might be potentially explained in several ways. So first of all, the lexical distance we were discussing so far, and other causes might be, for example, the difference in the label distribution, which is, for example, in the training where 67% of data are neutral, probably it is very likely to observe a bias toward this majority class. And another potential cause could be the robustness of the gold standard in terms of the integrator agreement, which is substantial to almost perfect for Stack Overflow and GitHub. And another possible explanation is the shared conceptualization of affect for the researchers who developed the GitHub and Stack Overflow datasets. So we developed our dataset in our own lab, and even if in the two labeling study we involved different raters, like for Stack Overflow we had 12 raters which were trained by referring to the shader framework of emotion. In our GitHub dataset we had three raters, so it's different people labeling different data, but still we hold as researchers from the same lab the same conceptualization of affect and the same interpretation of the very same theoretical model. So the guidelines for labeling are inherently inspired and guided by our research goals, which is something we need to consider when reusing tools. So as for comparison between supervised and lexicon-based tools, so the question is, should we use the one or the other? And we can see that in a within platform condition, supervised tools are hard to beat because, of course, the within training and testing condition is the optimal situation. So you have a gold standard from your platform and it is convenient to retrain. So it is not necessarily true if the training is performed in a cross-platform setting, and in some cases you might want to use lexicon-based tools. So going back to our second research question, this is, but what extent the tools agree with each other in a cross-platform setting, which means that what are we going to see if we use different tools? Do we end up with different conclusions regarding the labeling of our text for our study? So what we observe is that the results of the agreement study between two pairs confirm our previous finding regarding the agreement with manual labeling, because we see that, for example, in GitHub, the agreement drops from substantial and a within platform condition to moderate agreement in a cross-platform condition. And this is also confirmed for all the data set. So it seems like retraining using data from your own target platform is the way to go. So the problem now is, how many data do we need to label? Since manual labeling is very time consuming, this is an important question to answer. So to answer this question, we retrain the supervised tools in a within platform condition with incrementally bigger training set, and we always test on the same 30% partition we use in our previous study for comparison, for fair comparison. At every iteration, we increment of 5% the dimension of the training data. So here we have the learning curves for GitHub and Stack Overflow, and the straight lines are the performance of the lexicon-based tools, which never change because they're not retrained. So that's why they are always flat. So we can see that retraining is convenient compared to the performance of lexicon-based tools, and a nearly optimal performance is obtained already with a minimal size of about 1,200 documents for GitHub and Stack Overflow. A slightly different situation is observed for Jira, which is unbalanced data set, and in the case in this case, retraining is beneficial only with a larger set of about 1,600 documents. And anyway, the improvement over the centi-strength SC reference performance is negligible. And this might also be due to the fact the centi-strength SC was actually optimized by fine-tuning the lexicon and the rules on a subset of this Jira dataset. So to conclude, here are some lessons learned and which can inspire guidelines for safe and reliable sentiment analysis in software engineering empirical studies. So overall, our results are in line with our previous findings in the benchmark study we presented at MSR 2019, showing that software engineering specific tuning or sentiment analysis actually enhance accuracy. However, we recommend not to use software engineering specific tool as off the shelf, which means without retraining, because the results of our benchmark demonstrate how retraining across platforms do not work well for supervised tools. Thus, we suggest that probably the concept of domain should be narrowed down at the level of the specific platform. And we need to build a robust gold standard before retraining. So learning from balanced, high agreement data produce better results. And finally, in absence of a specific platform gold standard, unsupervised tool might be a way to go, might be a solution. However, in both cases, we recommend using a tool only if, after performing a preliminary sanity check, also to check whether, not only whether the tool produces satisfied results in terms of agreement with manual labels, but also to see whether the tool is in line with the research goal you have. Because one of the most dangerous assumptions when we're using machine learning AI tool, any components which is developed by other researchers, is that you are also implicitly inheriting the original goals and conceptualization of sentiment and affect of the creator of the tool, which might not necessarily align with your own specific goal. Some people might have in mind opinion mining, some other might want to detect specific emotion and so on. So that's basically it. Thank you for your attention, and see you at the question answering session at MSR.